Hi everybody, I'm Kiam from Bundeswehr University Munich, an AI-based planning framework for HAPS in a time-varying environment. I guess the most perplexing word here is HAPS. So what exactly is a HAPS? High-altitude pseudo satellite is a peculiar fixed-wing solar-powered UAV that flies in the lower stratosphere. It is lightweight and has extremely long endurance, up to a month and probably years. So the industry pledges that it can operate like a satellite, but with more flexibility for deployment and maintenance. However, given its build, being slow like a bicycle and fragile, it is extremely challenging to maneuver the platform. Therefore, the planning on a ground control station must be done carefully by considering weather forecasts, mission requirements, and of course also the platform dynamics in order to increase operational efficiency and safety. An example future deployment of hubs involve deploying several platforms at the same time with different kinds of sensors, be it infrared or electro-optical RGB cameras. The hubs are requested to monitor point of interest situated within a vast area. So different point of interest needs to be recorded at different time slots using a specific camera, either infrared or RGB, for example. The monitoring of this point of interest must be done while considering the varying weather condition and the forbidden airspace, which could also vary with time. And as you can imagine, with the speed that platform is going, especially the weather related obstacles must be considered dynamic obstacles. Furthermore, given the low speed of the area platform, it also implies that we need to consider the wind field. So this is a highly complex planning problem. If we break it down into fractions, what we face here is a combination of several typical planning problems like the motion planning problem, task planning for simple sequences of tasks like recording images and communicating data to the control station, as well as task planning for a time-dependent multi-vehicle routing problem. Let's look at the motion planning problem we are confronted here first, which is a kinodynamic problem. What we need to consider are the typical kinematic model of a fixed-wing aircraft in a vector field. The control parameters, which are the turn rates and the climb angles, as well as the time-varying constraints imposed by the static and dynamic obstacles in the airspace. And this can be projected as convex polygons on altitude at which the HAPS flies. So for dynamic obstacles which represent the dangerous weather zone over time, the parameters can be updated with linear relations over time. But instead of using a conventional motion planner here, we decided to use a PDDL plus planner. PDDL plus is a problem modeling language that offers the possibility to formulate mixed discrete continuous problems that can be leveraged to solve, on one hand, the kinodynamic path planning problem, which is continuous, and the task planning problem, which is discrete. So while task planning using PDDL plus is classic, solving a kinodynamic path planning problem with PDDL plus planners is not a usual thing to do. In this paper, we provided an overview of how to map conventional motion planning paradigm to the paradigm in the PDDL plus language. As a rough idea, so actions in PDDL plus are comparable to the control parameters, processes are comparable to state propagator, and constraints are comparable to state validity check. We're using this work ENHSP, which is a PDDL plus planner that was first published in 2016 that has heuristics to support nonlinear mathematical operations. Here you can see the path plan for HAPS from A to B over time using weather forecasts on the wind field and the dynamic hazardous weather zones. We also tested the plan successfully with a 6 degree of freedom simulator provided by the German Aerospace Center. So it was just motion planning that we have seen so far here. In the previous work, motion planning for HAPS was performed in 2 steps. So first, task planning at a strategic level, followed by motion planning at a tactical level. What we intend to achieve here initially was a tightly coupled task and motion planning by combining both search spaces. So on top of the kinodynamic motion planning problem presented just now, we also added in the PDDL plus problem model the task planning problem for multi-vehicles. However, we were confronted with a scalability issue. The domain independent heuristics of ENHSP have problems coping with multiple hubs and multiple point of interest. So instead, we took a step back from the tightly coupled task and motion planning problem, task and motion planning approach, but use an integrated task and motion planning approach. The idea is to embed the motion planning problem search space within the fraction task planning problem search space. Practically, what we do here is an interleaving task and motion planning architecture. So for this, we built on top of the PDDL plus planner a multi-vehicle routing solver based on adaptive large neighborhood search. The main role of the adaptive large neighborhood search is to assign point of interest optimally to the multiple hubs, while PDDL plus takes care of the motion and simple sequential task planning. This ALNS search is initialized with a plan and subsequently improved locally by searching for a better route in the neighborhood. The advantages of using adaptive large neighborhood search here as the wrapper of PDDL plus planner is, so once the iteration is initialized with a feasible plan, the implementation is almost any time, which means we can subsequently only find plans of better or same quality. The neighborhood search of adaptive large neighborhood search also breaks down the complex problem very naturally into smaller problems that can be solved by ENHSP. And finally, problem-dependent meta heuristics can be built easily into the adaptive large neighborhood search. The long list of meta heuristics used are described in the paper. So we ran some performance tests. First of all, what we observe is with the integrated task and motion planning method, we have higher success rate of generating feasible plans compared to the sequential task and motion planning method. And secondly, within the same plan horizon, plans generated by both approaches, they produce the same comparable plan quality. So in terms of the amount of rewards collected, or rather the number of point of interest monitored within the plan horizon. So as a future work, we intend to make this task and motion planning framework for off-the-shelf use by offering an interface for defining the problem-specific meta heuristics, as well as a generic method to tune the parameters of the adaptive large neighborhood search. So thank you very much for your attention. And if you have questions, please feel free to ask.